In this lecture, we're going to set up the language that will make probability theory rigorous. We will have to start with what are known as probability measures. For some of you, this might be review if you've taken a course in, let's say, maybe measure theory, or maybe you've even taken graduate course in probability. And for the rest of you, this may be something that's new. But in any case, it would be helpful to go through these definitions. And what we're going to be doing, this is going to be based on the work of Kolmogorov. And before we write down the definition, we need some intuition for what we're trying to do. The intuition here is that we want to define by what we mean by a random experiment. This is really what probability theory is all about. Probability theory is the study, you can say this is the study of random experiments. So one has to rigorously explain what we mean by a random experiment. Now, intuitively, random just means something that is unpredictable, something that you just cannot predict. The classic example is tossing a coin. If you toss a coin, there's two outcomes, heads and tails, and that is impossible to predict. If you give a coin to someone and you ask them to toss a coin for you, it is completely impossible to say what the outcome would be. And even if you're using a robot, even if you have a robot and even if you know exactly the kind of actions a robot takes, the issue is that the outcome of heads and tails is very sensitive on the initial conditions. So even if you're off by like 1/1,000,000th of an inch on the angle at which you toss, you would get a different outcome. So even if you were using a robot and not a person, and you knew how the robot was programmed to throw a coin, it still, practically speaking, is unpredictable. So intuitively, a random experiment, it's an experiment that every time you do it, you get a different result. Maybe you get the same result, but in general, it is something that's unpredictable. And what we begin here is, we begin with what is known as the sample space. Make the definition. Omega, this is going to be just a set, and it's called the sample space. And intuitively, this is supposed to represent the outcomes associated with a random experiment. That's what it's supposed to represent. So when you are tossing a coin, there will be two outcomes, H and T, heads and tails. If you're throwing a 6-sided die, you would have 6 possible outcomes. So the 6 numbers you see on the die. Now, these are finite sets, but this set could be infinite. And the most interesting examples is when the set is actually uncountable. When this becomes an uncountable set, and that would actually be the primary case that we're going to deal with when the sample space is actually there's an uncountable number of possibilities that can happen. I'll show you an example later on, but you can, like when you take an introductory course in probability theory, an undergraduate course, you often keep things simple and you assume that you have a finite sample space and you just count the number of possibilities that you have. But this idea, of course, generalizes to random experiments that can have an infinite number of outcomes. So that's the definition of the sample space. It's just a set and nothing more than that. It's, of course, supposed to represent the outcomes. So that is the sample space. But a sample space is not enough to quantify by what we mean by a random experiment. This is sort of like the first step. The first step is associated with a random experiment is the set of possible outcomes that can occur, and we call that the sample space. But I'm going to show you 2 random experiments with the same sample space that are fundamentally different. So here are two different random experiments with the same sample space. So the first one is, this is random experiment 1. And here you have a 6-sided die. And you see which of the 6 sides comes out. And the sample space would be the numbers from 5 to 6. Now, here is a different random experiment. So we're going to draw a pentagon like this. And we're going to turn it into a cone. Like that. So this is a pentagon, 1, 2, 3, 4, 5 sides. So you have 5 triangles, and then you have a base at the bottom. And you can label, so the numbers 1, 2, 3, 4, 5, these are on the triangles that you see. And 6, this is going to be the base. Okay, and when you write out the sample space here, it will also consist of numbers from 1 to 6. Now, some of you might be thinking that, is it not supposed to be the case that all 6 sides are supposed to be equally likely? Like, for instance, with a symmetrical 6-sided die, all of the 6 faces, they're symmetrical, so they're going to be equally likely. So when you toss them a large number of times, roughly 1 out of 6, you will see each of the 6 numbers. But here, this is not symmetrical anymore. You can see that the base, so here you might look at the side that is facing upwards. Here there is no up, but there is a side that is facing down. So maybe this 6-sided die lands on its base, but you can also imagine that it tilts over to the side and it lands on one of the 5 triangular faces. So instead of looking at the side which lands face up, there is no up here, but you could talk about which side it lands face down. And the sample spaces are exactly the same in both of these random experiments, but in this one, all of the 6 outcomes are equally likely, whereas in this one, even though we might not know exactly how much more likely is the base to occur than the other sides, it feels like the base should be more likely because it takes up a lot more area, and it's not really possible to figure out what the appropriate number would be because it very much depends on the geometry of this cone. You can imagine that if this cone was probably a lot taller, it would be more unstable on its triangular faces, and so it will probably land on its base more frequently. And you can also imagine that if this tip was pushed further down, so it was flatter, then maybe it could be more likely for it to land on its 5 triangular faces. So the likelihood of landing on, let's say, the base will probably depend on the geometry here. But I think we can agree that these are not equally likely, and so these 2 sample spaces, they're the same sample space, but somehow these 2 random experiments are fundamentally different from each other. They behave very differently. So a sample space is not enough to define what, so it's not sufficient to describe a random experiment. We need something else. So the distinction is really going to lie in the following. Let's say E, and we call this an event. So an event is just a subset of the sample space. It's some outcome you're interested in seeing. So let's say this event will consist of the even numbers, 2, 3, and 6. And here we have another event. It's the same event. And it also consists, this should have been a 4. It consists of the even numbers, 2, 4, and 6. Well, here the probability of the event, you would just count. You would just say there's, so this is supposed to represent the probability of the event. This is what we want to define, by the way. But intuitively, the probability is supposed to measure how frequently you see the event takes place. This is supposed to represent that if you were to do this random experiment like a billion times, then how frequently would you see this event take place? How often will this event be satisfied? And it makes sense because there's three outcomes in here and there's 6 outcomes in total, that it should be 3 over 6. So this just makes sense by like a symmetric kind of an argument. This is what you're supposed to get if you were to perform this experiment like a billion times, you would get about half of them would come out to be an even number. So that makes sense. However, here, I do not know what the probability of the event is, because the probability of this event will depend on the geometry of the cone, and it will depend on how much area the base takes up. But whatever this is, because 6 is more likely to happen than these 5 numbers, it should not be, like, they're not equally likely. This number is supposed to be more. So it has to be bigger than a half. Like, I might not sure exactly what the number is, but it certainly has to be greater than a half. And this is really where these two, like on the level of probability, this is how you distinguish between these two random experiments. In this random experiment and in that random experiment, the sample space is exactly the same. But what makes them fundamentally different is that when you try to calculate the probability of an event, you're getting different calculations. So you have to take, you need some way of measuring the probability of events. And this is going to be the motivation for the definition that we're about to write down. So I'm going to begin with the wrong definition, and then we will clean it up as we go along. This is going to be the wrong definition. Now, of course, there's no such thing as a right and wrong definition. It's just a definition. But what I mean is this is not the way it's defined in a book. And I'm intentionally doing this because I want to start with the first thing that comes to mind, then we notice the problems, and then we build upon that. So here's the wrong definition. So let omega be a set, be a sample space. We can assume it's not empty. We're not going to make a big deal about that. So this is a sample space, not empty. And a probability measure let's call it P, is a function that takes subsets of the sample space. So when you talk about events, you talk about subsets of the sample space. So it takes a subsets of omega, and it assigns them. So when you take a subset, what do you assign that subset to? You assign that subset to a number between 0 and 1. 0 is supposed to represent 0%, 1 is supposed to represent 100%. So you're going to assign it to the interval between 0 and 1. So it maps, you take the subsets of the sample space, and then for every subset, you assign it to a real number between 0 and 1. So intuitively, this is supposed to represent a function that calculates for you the probability, like the chances of seeing a particular type of event that takes place. So a probability measure, it's a function which satisfies the properties. So the first property you want to say is that the probability of the entire sample space should be equal to 1. And the probability of the empty set should be equal to 0. Though, as you're about to see, this is going to be a consequence of that. It's going to be the consequence of the next property. And the second property will say that if E and F are disjoint events, non-overlapping events, then the probability of their union should be equal to the probability of their sum. And then from here, you're going to have a corollary. So there's an immediate consequence from these definitions, is that it follows that the probability of a complement has to be 1 minus the probability of the original event. The proof here is very simple. The proof will go as follows. So you just observe that the probability, let me write it like this, that if you take any event and you take its complement, then the event and its complement are disjoint by definition, and together they give you everything. And so if you calculate the probability of the left, that would be equal to the probability of the right. But the probability of the sample space is 1. That's one of the requirements of being a probability measure. Probability of the entire space has to be 1. So this is equal to 1. Okay. And then it follows from here, because these two are non-overlapping, that the probability of E plus the probability of the complement have to give you 1. And now if you solve for the probability of the complement by moving this to the other side, you get the corollary that the probability of the complement is 1 minus the probability of the original event. So you can really see that this one is redundant. You do not have to include this, it will follow, but I like to write it out anyway, just to enforce this property. It is an important property that's used a lot. So I'm not saying that the definitions I write down on the board are written to be in the minimal sense, like where none of the parts follow from any of the other parts. We're not trying to be efficient here, we're just trying to develop the subject. Now, as a homework problem, and like I said, you will see homework added at the end of each video lecture. So at the video description, you will see some homework problems for you. So here is a homework problem. So assuming we have a probability measure, here's a homework problem. You can think about this. So suppose P is a probability measure on a sample space. You have to understand the probability measure is not actually defined on the sample space. It is rather defined on the subsets of the sample space. So this is the way we say it. So we have a probability measure defined on a sample space, and you want to show the following. So the first one you can show is for any two events. So an event is just a subset of the sample space, E and F. We have the following result, that the probability of their union is the probability of their sum minus the probability of their intersection. This is sometimes called the inclusion-exclusion principle. It's used quite a lot. By the way, if you're bothered when I keep on saying the word probability, if you're bothered by this, all it means is we have a function. Probability is a function that assigns a real number between 0 and 1 to an event. And an event is just a subset of the sample space. So that's all what probability means. It's just a function that maps events to the unit interval. Okay, that's all it is. Now, intuitively, this is supposed to represent the chances of an event taking place in a random experiment. That's what it intuitively is supposed to represent. But formally speaking, that's all what it is. So by using the two properties that we mentioned, these two properties that we mentioned, you want to derive what is known as the inclusion. This is the inclusion-exclusion principle or formula, whatever you want to call it. Another thing you can show is, this is another property you can say, is that for any two events, E and F, the probability of their union will always be dominated by the probability of their sum. Another one you can show is that if an event is contained in another event, then the probability of E has to be less than or equal to the probability of F. Okay, that would be, this one is sometimes called the monotone property, that if you have a bigger event, you have a bigger probability. The one in the middle is sometimes called sub-additive property. So it's sub because it's smaller. It's sub-additive. Additive would mean The probability of the union is the sum of the probabilities. But it's only additive when the events are disjoint, as you can see. When the events is disjoint, it's additive. But in general, it's subadditive, that it's less than or equal to that. So these are some of the basic properties. Now, let me write down a very simple proposition. Now, before I write down a proposition, maybe I should show you an example. Okay, so like in real life, the probability measure is not given to us. So only in mathematics do we start with a probability measure as a given, and then we work from there. But if we're doing applications in real life, we often have to create the measure ourselves based on what we think makes the most amount of sense. So, for example, if we toss a fair die, six-sided die, then the sample space would consist of numbers from 1 to 6, and it is reasonable to define the probability measure as follows. So this is how you would define it. You would say the probability of an event is equal to, and this is by definition, so you're defining what it is. So this is the reasonable way to do it because you're trying to model a phenomenon you see in real life. So the reasonable way to do it is you have to declare how you're calculating the probability of an event. Well, what you would do is you would count how many numbers you have in the event, and then you would divide out by 6, right? So it would be equal to n divided by 6, where n, this is just the how many elements are in E, right? That would be the reasonable way to do it. And you have to verify that all of the properties of a measure, of a probability measure, are satisfied. So one of the properties that we want is the probability of the entire sample space has to be 1, which it is, because it will end up being 6 divided by 6, which is 1. If we go back to the other example, so if we toss a cone-shaped six-sided die, then the sample space is going to be the same as we've said, from 1 to 6. And one possible way, now I say possible because like I indicated, in this case, the geometry of the cone will dictate the correct way to compute probability. But here's like one possible way to do it. So one possible way to define P is you would do this. So let me draw a picture for you. So we have our cone. So maybe the base happens with 50% of the time. For example, let's say it takes up a lot of area. It's 50% of the time. And it's more stable and all of that. That means the remaining sides should take up 50% of all of the outcomes, but there's 5 of them. So every one side should therefore happen 1 out of 10. So therefore, one possible way to define P is as follows. The probability of an event is going to be equal to n divided by 10 plus m divided by 2. And what is n and m? Where n, so that would be how many elements from 1 to 5. So you would just take the event and you would intersect it from the numbers from 1 to 5. So you would see how many numbers you have from 1 to 5. And m would either be 0 or 1, depending on whether, so you can just say it's E intersected with the number 6. So when you intersect it with the singleton set, either this is going to be 0 if it omits the number 6, the base of the cone, or it's equal to 1. So this number will either be 0 or 1, and this number will be from 1 to 5. And by doing that, it's easy to see that the probability of the entire sample space will then add up to be exactly 1. And then you have to verify the property that the probability of a disjoint union would then be the probability of the sum. So this will be one reasonable way to do it. And if this is incorrect, then you would just adjust the number. So maybe the base does not happen a half of the time, maybe the base happens a third of the time, and then you would appropriately adjust the other numbers. So that's the way you would do it. So you can see that when you're doing probability theory, the probability measure is given. But in applications, it is not given, and you have to conjure it up in a way that you think is reasonable. But regardless of how you do it, it has to be done in the way to satisfy the properties of a probability measure. So that's just an example. Now, let's get to a proposition here that's fairly simple. Proposition, let P be a probability measure defined on a non-empty set on omega, which we call the sample space. And let E1, E2, En be events. So events, these are just subsets. These are just subsets of the sample space. And these events are that are pairwise disjoint. So pairwise disjoint means that if you take EI and you take EJ and you intersect them and you get something that's empty for all I not equal to j. So if you take two different events, they have an empty intersection. So then the probability of their union, if you want to be fancy, you can also write it like this. You would just write union I from 1 to n of EI. That would be equal to the sum of all of these events, the probability of all of them. And proving this is actually fairly simple. You can try doing this yourself. So maybe I'll put this as a homework problem. It will follow from the definition that we gave for a probability measure. So you can try showing this. Now, what I want to show you next is, well, maybe I should say where we're going with this. Often in mathematics, especially analysis, we often like to deal with infinite sequences. Right? We use that all the time. We prove something by constructing an infinite sequence, then the infinite sequence converges, and the thing that it converges to is the solution to our problem and all that stuff. We do that all the time in analysis. So being consistent with that theme, you may wonder, is this true if you have a sequence of events that are pairwise disjoint? Will it be true that the probability of their union is then equal to the sum of the probabilities? So this is a warning. If P is a probability measure on space, and if you have a sequence of events, let's say we start our index at 0 as we normally do, are pairwise disjoint events, then if you were to take the probability of their union, this not necessarily is not necessarily equal to this sum, the infinite series. So the infinite series of their sum. And you can come up with pathological examples. So I'm just going to say that you can find such pathological examples in a real analysis book. So in a real analysis book, they're not even talk about probability measures, they just talk about measures. And if you want to know the difference between a probability measure and a measure is, the distinction is that a probability measure is supposed to give you 1 on the entire sample space, whereas a measure does not have that requirement. It just has to give you a non-negative number. It does not have to be between 0 and 1. It just has to give you a non-negative number. So that's what a measure is. And you can find examples in a real analysis book where you have a measure, not even a probability measure, but you have a measure that's defined on the set, on the subsets of a set, and it could satisfy the properties that you want. But when you hope that it works on this sequence, the sequential union, you have a sequence and you take the union of all of that, then that is not necessarily equal to this anymore. So things can go wrong. And the reason for this is because this is essentially a proof by induction. So when you do this, this is a proof by induction. And whenever you have a finite collection, the way you reach a finite collection is doing it 1 at a time. But when you have an infinite collection, you cannot obtain an infinite collection 1 at a time. You have to sort of take all of it together all at once. So because of that, you're not able to turn this previous proof, which is rather straightforward when you try to do it, into this kind of a property. And this is a bit problematic because we often like to work with infinite sequences, and we want to be able to pass from a union to a sum. That would be a desirable property to have. And I also want to show you some other issues that happen. But first, I'm going to give you a definition which is closer to what you see in the book. So let us fix our previous definition. Okay, so let's write down our previous definition. We've said that a probability measure on a sample space, omega, let's call it P, satisfies the properties that the first property is that if, well, the first property is that the probability of the entire sample space should be 1, and the probability of the empty set should be 0. And the second property is that if E intersect F are empty, then the probability of their union should be the probability of their sum. So if that property is satisfied, yeah, so we want this property to be satisfied. So these two, this was the first definition that we gave, and this definition is a little bit problematic. So we're going to fix this definition, and we're going to change this. We're going to say, and this is still the wrong definition. This is still wrong. And I'll show you the other problem with this definition. So a probability measure on a sample space will satisfy the following properties. That we will have these properties, but this we're going to change this, and we're going to rather say that if En are pairwise disjoint, if you have a sequence of pairwise disjoint events, then the probability of the union of all of them would be equal to the sum of the probability of the sum of their probability. So in particular, we're saying that this infinite series, which is an infinite series of non-negative numbers, that this infinite series converges and it gives us the probability of their union. So we want this property to be satisfied. So basically, this is the, you can say this is the additive property on sequences, on pairwise disjoint sequences, as opposed to the additive property on just a pair of disjoint events. Now you can see that this definition, it's stronger than the previous definition because it includes the previous definition. And the reason for this is because if you have two events, E union F, and you want to, and let's say they're disjoint, then you can just turn this into an infinite sequence by just keep on taking unions with the empty set, like this. So then, because this is a pairwise disjoint collection, because the empty set is already disjoint with everything else, the probability of the union would then be the sum of the probability. So then this would just be the probability of E plus the probability of F plus the probability of the empty set plus the probability of the empty set, and so on. But the probability of the empty set is 0, so this will drop out. And you end up getting, of course, the probability of the union is the sum of these two. So the finite case is included in this more general case where you have sequences of the pairwise disjoint events. You can see we actually need, so I think here in this definition, this one, unlike the previous one, does not follow from these two. So what I'm saying is, let's suppose I told you the property 1 only this, and property 2 to be only that, then I do not think it will follow that the probability of the empty set has to be 0. It's something you can think about whether or not you actually need to put that into the definition. We really do not care. We want to get to stochastic processes at some point. That's probably a more appropriate question to think about when you talk about like foundations of probability theory and which of those conditions you actually need, which of them you do not need, under which case can you relax them, and things like that. So let's not worry about that. Okay, so now I told you that this definition is still wrong. This is still the wrong definition. There's still something problematic with this definition. So let me show you an example, a very interesting example that goes wrong. Example. Let us try to, let's say, describe the random experiment of spinning a pointer on a circle. This is an interesting example. It will have some unusual properties about it, and it will make you appreciate the way the definitions are and why we make it that way. This is sort of like a game of roulette. In the game of roulette, you have a disc, and you cut it up into many pieces, and you have a number in each piece. But this is a different type of random experiment. You have a circle, and then you have a pointer, and you spin this pointer randomly, so it kind of spins around like on a roulette wheel, and then it stops. And then it stops at a certain number, and whichever number that it lands on, that is your outcome. Now, of course, this is not the type of experiment you can really do in real life, because in real life, the pointer does not have, it's not infinitely thin. When we draw lines in math, they are infinitely thin. And when we land on a point, it has no size, whereas in real life, anytime we draw a point, that has size. So it's sort of like an idealized mathematical experiment that can exist in your head, but it's not something you can really perfectly recreate in real life. You can get close. You can make these really thin, but then it's sort of like a roulette wheel that you're approximating discretely. This is an idealized situation where you are located at each point. So this is the random experiment, and let's first describe the sample space. The most convenient way of describing the sample space is to use Euler's identity. That e to the I theta is cosine theta plus I sine theta. And so every point on the circle can be represented in this form. So if you pick a point on the circle, it can be described as e to the I theta, and it can also be described as e to the I theta plus 2 pi. That will denote the same point. The angle might not be unique, but the point is unique. So you're uniquely describing a point on a circle once you put it in this form. The only thing is the angle might not be unique, but that's okay. If you look at the complex exponential, that will uniquely describe a point for you on the circle. So we can therefore say that the sample space will consist of complex numbers whose norm is equal to 1. So every one of these complex exponentials, their norm, if you were to calculate the absolute value of this, you will get cosine squared plus sine squared. That would be equal to 1. And conversely, any such complex number with norm 1 can be written in that form. It's kind of interesting. When we were doing topology, this was a very important topological space for us. But now we're doing probability theory, and we're using the exact same space, except we're not calling it S1, which is the way we normally describe the one-dimensional sphere, but now we're calling it omega. So this is going to be our sample space. And how should the measure be defined? Now, one thing I want you to notice about this random experiment is that an individual sample point in this random experiment, each individual sample point, in other words, the event, the singleton event that contains a single point, should have probability equal to 0. Which, when you first see this, it looks very unusual, because whenever you see the sentence probability equal to 0, you're thinking of an impossibility. But this is not impossible. In fact, when you spin, you land somewhere, and the point at which you land will have probability equal to 0. So how can that possibly be? Well, the explanation here is as follows. That imagine you spin the pointer 1 billion times. We expect to perfectly land. I know that in real life, there's no such thing as perfectly landing on a infinitely thin point on a circle, but this is like an idealized experiment, that we perfectly land on this event. I'm writing set z instead of z because events are subsets of the sample space. They're not elements of the sample space. That we perfectly land in this event, we expect to perfectly land, so not close to z, but exactly on z, we expect to land 0 times. But even if you do manage to land on z, that would be 1 time out of a billion, which that ratio is close to 0. Now, if you were to increase this number to a trillion, you still expect to land 0 times. But even if you manage to somehow, by miraculous, to land twice, that would be 2 out of a trillion, which will be even closer to the number 0. And whenever we're talking about probabilities, we're asking the question, if we were to do the experiment n times, where n goes to infinity, how many times do we expect to see it? And the answer is 0, right? That ratio should be 0 as n goes to infinity. So even though it could potentially happen, that ratio will still go to 0 if it's not already equal to 0. So that's the only sensible way of describing it. So here's the interesting. Here's something interesting about this. So this is why probability measures are defined on events, not on sample points. Okay, so you do not realize this if the sample space is finite. If we go back to our example that we had with the dice, and we had 6 possible outcomes, and we said that this outcome was 1/2 of the time, and each of these were 1/10 of the time, you might get the incorrect impression that in order to define a probability measure, it's enough to give a number for each sample point, and you do it in such a way so that the numbers add up to 1. And then if you want to calculate the probability of an event, you simply see which of these numbers are in the event, and these are the associated fractions that you have to add up. And by adding them up, you will then get the probability of the event. The problem is this kind of approach does not work for this random experiment, because this random experiment is a lot more complicated. It has infinitely many possible outcomes. And every single one of these outcomes, every single one of these individual points, the probability of a singleton should happen with probability 0, yet somehow the probability of landing somewhere should be equal to 1. So this shows why in the definition the probability measure is defined on events and not on sample points. Defining the probability measure on sample points and then extending that to events makes sense in some very simplified random experiments. Like, for instance, when you have a random experiment that only has a finite number of possible outcomes. But in general, that is not the way to do it. So that should make you appreciate the definition a little bit more in why it's defined on events and not on sample points. But then there's another bizarre property of this random experiment that I would like to show you. So, okay, so let me take this away. It's often convenient to imagine events which are easy to visualize. So in this case, an event which is easy to visualize is something called an arc. So this over here, that would be called an arc of the circle. If you want to have a rigorous definition of an arc, you can just define it to be a connected subset of the circle. But then you have to give the circle a topology, and you have to know what it means to be connected. If you do not know what that means, then you can, okay, so maybe you can say connected would mean, so like the reason why this arc is connected is because if I pick 2 points, I can then find a path between them that stays within your set. But if you have, let's say, something like this, so let's remove this. So let's say we had, let's say E was this. Then you can see the problem that there's no way that you can travel from the 2 points. You will have to leave your set. So that's one way you can define connected. But I assume you know what I mean by connected. So we can say an arc is a connected subset of the circle. So we allow, in the definition of an arc, we allow the empty arc, the empty set, and the entire circle that's like the trivial arc, the whole thing. So that's what we mean by an arc. And it could be an open arc, it could be a closed arc. So we can talk about an arc where you exclude the endpoints. You can talk about the arc where you include the endpoints and things like that. So these are connected subsets of the circle. And so these are easy to visualize. So it is reasonable to set the probability of an arc, let's say A is the arc, the probability of an arc to be equal to, so let's say we have an arc. Okay, so this is an arc. Okay, so let's say this is our arc. And I was to ask you, what is the probability of landing inside that arc? Well, the reasonable way to do this is you would just measure how long the arc is, and then you would divide the length of the arc by the length of the circle. So you would take the length of the arc, and you divide it by the length of the entire circle. And the entire circle, this is a unit circle, so its length is 2 pi. This is the reasonable way to do it, right? It's the ratio of this length to the entire length. Now, if you want to be one of those people who likes to go off topic, you can wonder, how do you rigorously define what the length is? Basically, what you would do is, let's say you have an endpoint and you have another endpoint, assuming you have endpoints, and this is like e to the I alpha, and this is e to the I beta, and then you would have to pick alpha and beta in such a way so that the angle change between them is smaller than 2 pi, and then the length of in radians, the length of an arc is equal to the angle, the central angle of the circle, and so you would just subtract the 2 angles. So that's sort of the way you would do it. So if you're wondering how does one rigorously define length, that's like a quick outline of how to do it. But I really do not want to get into that because that's like off topic, and we're trying to focus on the probability of this and not on geometry. Of course, I understand that one is trying to develop math in a rigorous way. You want to be able to define things very clearly, but when you're no longer working in probability theory and you're sort of deviating to a different area of math, then you probably do not want to do that. You want to kind of stick within the world of probability theory, since this is what the theme is about. And defining this in a rigorous way, that would be more like geometry. So we're assuming we know how to define this. So that would be the length of an arc. And then the probability of landing within the arc should be equal to, right? This is the reasonable way, because when you spin, the only thing that matters is how big the arc is. So it is reasonable to define the probability of an arc to be this. And we also want, it is also reasonable to assume that the probability measure is rotation invariant. So in other words, let's say we were to take this arc and we were to rotate a certain amount. So we were to take the exact same arc and we were to rotate it. So that would mean that if you have, so if this is, so in this case, we would just write e to the I theta times a, where theta is the rotation. It's the rotation that's being applied to this arc. So this just means you take this complex number and you multiply every element of this set. So you're rotating every element individually, and so you're rotating the entire set. So in other words, so to be more precise about this, i.e., for any event E, we have that the probability of an event when you rotate that event should be equal to the probability of the original event. You might wonder, does this second property not follow from the first property? Because if the probability of the arc is determined by the length of the arc, then is it not true that if you rotate the arc, then the length remains the same? That is true, provided that the event happens to be an arc itself. You can imagine this event could be something very complicated. So, like for example, you can have, just to show you what I mean, maybe the event will consist of complex numbers of the form e to the I theta, where theta is an irrational angle. And then if you were to draw a picture of this event, it's just going to be a bunch of scattered points everywhere. So like the points that are described by an irrational angle. So it'll be just points everywhere. And it will not be an arc, it'll just be a bunch of scattered points. And it's still reasonable to expect that even though you do not have an arc anymore, when you rotate that, it should remain rotation invariant. Okay, so now here is what we claim. So we argue that it is impossible to define a function p that takes us from events, so just subsets of the circle, it maps us to 0, 1, and satisfies the following properties. So the first property is probability of the circle should be 1, probability of the empty set should be 0. The second property is that if En are pairwise disjoint, then the probability of their union should be equal to the probability of their sum, the sum of their probabilities. The third property is that if A is an arc, so this is a very special type of event, then its probability should be determined by its length. You would just take the length of the arc and divide it by 2 pi. And finally, for any event E and any real number theta, we have that if you rotate the event by this angle, the probability of that should be the same as it is before. So it is impossible to satisfy all of these conditions, which is a bit, now this might worry you a little bit. It feels like you should. Now, before I show you why it is impossible, I'm going to give you what we do. So normally what we do in a situation like this, the complication arises. I'm going to show you where the entire problem arises. It arises right over here. Because you're talking about all subsets of the circle. And you probably heard of this, it's called the power set. The power set of the circle. And there is a famous result in set theory that if S is a set, then the power set of a set, the cardinality is strictly bigger than the cardinality of the set itself. So this cardinality means there is no bijection. We talk about countable sets, we talk about uncountable sets. So for example, if S is a countable set, then the power set will be an uncountable set. It will have cardinality that is strictly bigger than the set itself. And when we're talking about the circle has cardinality of the real line. Because you can just imagine taking the circle, cutting it, and opening it up to be a line. So the circle is in one-to-one correspondence with the real line. But this is a large set, and the power set of that is even larger. And there's a theme in mathematics that the larger your set becomes, the more unusual things become. So, and this is kind of where the issue arises. We're sort of working with every conceivable subset of the circle. And that's where we have a problem. So usually what we do, instead of working with all subsets of the circle, we work with a smaller collection of subsets. And you're going to see that in the definition of a probability measure. The probability measure in general, unless you have very simple examples, is not defined on all subsets of a sample space. It is in general defined on a smaller collection of subsets. This is to prevent certain pathologies from arising. If you think about this, I mean, a great example of this, when you learn about integration of functions, you cannot integrate any function that you can possibly think of. You usually restrict the collection of functions to a smaller collection, which is just large enough that you can do things with it, but it does not include every conceivable function. If you allow every conceivable function, you will have some strange pathological situations that occur if you try to do integration. So it's sort of similar to that. Instead of working with every subset, we're going to use a smaller collection of subsets for which things behave well. But I want to show you the issue that happens if you consider every subset of omega. And this example is a nice example to show you why the definition is made the way that it is. So here's how we're going to do it. We're going to prove. So we're going to do, this is going to be a proof by contradiction. We assume that this is possible, and we arrive at a proof by contradiction. So let us define an equivalence relation. And we usually use a tilde for an equivalence relation on the circle as follows. So we say that 2 points, so 2 complex numbers on the circle, are equivalent. Z is equivalent to W if and only if we divide them, Z divided by W. So, by the way, I should explain that so these are complex numbers with norm 1. And if you divide them, the norm will remain 1, because 1 divided by 1. The norm will remain 1. So this is, again, so this is, of course, on the unit circle. And because it's on the unit circle, it can be written as e to some angle, e to the I of some angle. Let's call it Q for some rational angle. Okay, so basically, to put it simply, Z and W are related by a rational rotation angle. Okay, so the picture here would be that if this is Z and this is W, and we're saying Z over W is equal to E to the I theta, then that would mean that Z is equal to W E to the I theta. I'm sorry, not I theta, IQ, and then that would mean that you can find the rational number Q that will rotate this one to that one. So you can find the rational number to you. You can also find an irrational number that will do that for you, because you can always replace Q by Q plus 2 pi. But that does not contradict the definition, because we're saying for some rational number. It is possible to relate them to each other by using an irrational rotation as well, but we're just saying there exists a rational rotation. So that's what that means. And of course, you can see that if Z is related to Q, then Q is related to, I'm sorry, if Z is related to W, then W is related to Z, because you can just flip the fraction over, and then you will replace Q by negative Q. And it's also very easy to show that if Z is related to W, and W is related to another complex number, then Z will be related to that third complex number. And Z is, of course, related to itself by using rotation angle 0. So it's very easy to verify that this is an equivalence relation. So you have constructed an equivalence relation on the circle. Okay, and then what do we do next? So here's what we do next. So let E consist of, well, maybe to make it easier, okay, I'll make it a little bit easier for you. What we're doing right now is a little bit hard to understand because we have an enormously large set. We have an uncountable set. But to make it a little bit easier for you, let's say we take the integers. The integers, if you work mod 3, you divide the integers into 3 different classes. So these are integers that are divisible by 3. Then you can divide the integers into the ones that have remainder 1. And then you can have the ones that leave remainder 2. Like this. Okay, so these are the equivalence classes. So if you consider, so if this is your set, if this is like your sample space and you're working mod 3, so 2 integers are related if and only if their difference is equivalent mod 3, then these are the equivalence classes that you get. And then you can pick, and it does not matter how you do this. You pick, let's say, this one over here, you pick this one over there, you pick that one over there. So you just pick exactly one representative. So this is called a representative. So you're choosing exactly one representative for each equivalence class. Okay, that's what you're doing. So in this case, you would end up with the set E consisting of 6, -5, and 2. So you will have an equivalence, you will have a representative for each class. So that would be one way to do it. There's a different way to do it. You can also do it like this. And if you do it like this, then you end up with a different collection. Then you end up with 0, 4, and 8. It does not matter how you do it. The point is to do it somehow. And this is what we're going to do here. We're going to say let E consist of a single representative from each equivalence class. And this is a difficult set to understand because it's actually an uncountable set. I will leave that for you to think about. We do not really need this. E happens to be an uncountable set. And you can think about why that is. We will not need that, but it just happens to be uncountable. But that's basically what you do. You have your equivalence relation, and then for every equivalence class that you form, you pick exactly one representative for that class. Okay, so now we're going to, so here's what we're going to observe. So observe that if Q is a rational number and not 0, then if you rotate this event by Q, then that would be disjoint from the event itself. So why is this? So I think maybe it makes sense to leave this as a homework problem, but basically, if we take a point, so how do I want to say it? Like, so say that Z, so maybe I'll prove it to you. So let's say Z is in E, and Z is in here. Okay, so then Z can be written as E to the IQW for some W in E. And since Q, but then, what does that mean? It means that Z is equivalent to W, right? Because Z and W are related by a rational angle. So then they're related to each other. Now, this is impossible. This contradicts the fact that, well, maybe I should say this. So at the moment, there's no contradiction. So since Q is not 0, I mean, of course, if the angle is 0, then these two are exactly the same, and then the intersection is not empty. But because this angle is not the 0 angle, Z and W is not the same point. Z is not equal to W. And so, I mean, if you're wondering, by the way, maybe Z and W are still equal to each other. Maybe this Q is 2 pi. The problem is 2 pi is not a rational number. So it's kind of interesting. We actually need to know that pi is not a rational number in this proof, which is one of those rare situations in math where you actually need to use the fact that pi is irrational. But that's well known. I mean, I guess we can go off topic and talk about why pi is irrational and then prove that. But here we're using the well-known fact that pi is irrational. So if you, I mean, you cannot have like pi or 2 pi or 4 pi or anything like that. So Z and W are not the same. So they're two different points. And so Z and W are two different representatives, are two different points in different, because they're different, so they have to be in different classes. And so it means Z and W are not related to each other. Okay, so we have a contradiction. We're saying they are related to each other, and now we're saying they're not related to each other. So where does the contradiction come from? It came from here by assuming these had something in common. So a similar argument will show that if Q1 and Q2 are rational numbers, and Q1 is not equal to Q2, then this rotated set and this rotated set will be disjoint. Thus, the collection of rotations is a pairwise disjoint family. So what do we get from here? Thus, that would mean that the probability of the union of all of them would be equal to the sum of the probability of all of these. So let me explain this. Here we are using the fact that the probability measure is countably additive on pairwise disjoint on a pairwise disjoint sequence of events, which is exactly what we have. It's countably additive. This is countable. The rational numbers are a countable set. This is a countable set. Okay, so the probability of this countable union would then be equal, and these are pairwise disjoint, but therefore has to be equal to the sum of their probabilities. Now, you might be a little bit worried because when you have an infinite series that's indexed by the rational numbers, you might be a little bit worried about the ordering of the sequence, because when you have an infinite sequence of numbers, the way you order the sequence does matter in the kind of sum that you get. But you have to understand that these are non-negative numbers. So this is a absolutely convergent series, and there's no issue like that. So if you were thinking about it, it's not a problem. So, but here's what this is. This is actually the whole thing. This is the entire set. This is equal to the entire sample space. Let's think about why that is. Because the event, it consists of a single representative for each class. So if you choose a single representative, well, if you pick a point on the unit circle, that point is located in some class. And so so that means there has to be some number in E that point is related to. But if it's related to that point, then it means there's some rational rotation at which that point, when rotated by that angle, will give you the point on the circle. So I leave that for you to write out the details, but this just follows from the definition of how this was constructed. So what do we have? We have that this sum, this countable sum, oh, and I should say, what is this? We're assuming that our probability measure is rotation invariant. So this is just equal to the probability of E without the rotation. And now let's put everything together. So hence, the sum, the countable sum of the probability of this event has to be equal to the probability of the sample space, which is 1. So this is equal to 1. And we get a problem here. So either the probability of the event is 0, right? Either the event has 0 probability, which can happen, as we mentioned. Sometimes you have events that have 0 probability. And then we get that 0 is equal to 1. Right? This would then be 0, and that's equal to 1. Or otherwise, the probability of the event is some positive real number. It's a number between 0 and 1. So let's say it's a positive number. And then we get infinity, right? Then we get the, well, you can also say this is not convergent, whatever you say, but then you end up something like infinity is equal to 1. Because then you're adding a positive number infinitely, countably many times. So then this series diverges, it cannot be equal to 1. So regardless of what you do, we have a problem. So this shows, if we go back all the way at the very top, it shows that this random experiment of spinning around points on the unit circle, it is not possible to define a probability function that will be defined on every possible event. And so the compromise that we do is we want these properties to continue to hold, but the compromise that we do is we simply restrict the collection of events to something that's a little bit smaller, and then in the end, things behave in a nicer way. Just like in analysis, we often restrict to a smaller collection of functions, and we work with that instead. So let's make some definitions. So let's start with this definition. Let omega be a set or a sample space. It does not matter. An algebra on sigma. Now, I want to caution you a little bit is that this is not the kind of algebra that you do in an algebra class. It has nothing with that whatsoever. But you'll see why we call it an algebra. It's going to mimic a lot of the things that you're familiar with. So an algebra on a set, we have, let's say, a non-empty set. Let's call it, so how should we call it? Let's call it script A for algebra. Satisfies the properties. So we want the empty set to belong to our algebra, and we want the entire set to belong to our algebra. I forgot to say, this is a sub-collection. This is a sub-collection of subsets of the sample space. So you can always use the power set as an algebra, but we usually work with something smaller. So it's a sub-collection of subsets of the sample space. We want the empty set and the entire set to belong to our algebra. As you will see, some of these are derivable, so this is not a minimal definition, but that's okay. Then we would say that if E and F belong to the algebra, then their union belongs to the algebra, and their intersection belongs to the algebra. Oh, and I should say one more thing. I forgot to say this. If an event belongs to an algebra, then we want its complement to also belong to our algebra. Now, why do we call it an algebra? Because unions and intersections, they remind you a little bit of the properties of addition and multiplication. So for instance, if you have A union B intersect C, you can distribute the union over the intersection. And you can also do it the other way around. You can have an intersection here, you can have a union there. So intersections and unions, they satisfy a distributive law. And then the empty set, it plays a role as an identity element for union, because if you take the union with the empty set, you're not changing the union. And the entire set, it plays the role of an identity element for intersection. If you intersect with the entire set, you just get back the set that you started with. And this one plays the role of an inverse, that if you have an event and you have the complement of the event, then their intersection gives you what? It gives you the empty set. And if you have an event and you have its complement, then their union gives you that one. So it's almost as if you have addition and multiplication, and you have existence of inverses, and you have an existence of identities. That's why we call it an algebra. It's not like the typical algebra that you're used to. It's a different type of algebra. This is an algebra of sets. Sometimes this is called an algebra of sets. Okay, like this. And like I remarked, some of these are redundant. Like, for example, if you know property 3, you can drop this one. Also, if you know that it's true for unions, you can show it's true for intersections by using the negation rules for unions and complements. So this is not the optimal way of writing down the definitions, but we use these properties all the time, so let's just write it like this. That's what we call an algebra on a sample space. So now we're going to modify this definition a little bit, and we're going to change this just a bit. So this is what it means to be an algebra on a sample space. So now we're going to change this definition, and this is something that's a bit stronger. This is what we call a sigma algebra. So a sigma algebra, it's just like the algebra, but you want to interpret the sigma as the word countable. So people use sigma to denote countable. This is what you're basically saying, this is a countable algebra. So and you can probably guess what you think it means. It means that this is still true, this is still true, and you're just going to change these up. You're going to say that if you have a family of events and each En belongs to your algebra, then the union of all of them and the intersection of all of them, and again, one of these is redundant, both belong to your algebra. And because the empty set is included in the algebra, it means that if you have a sigma algebra, you have a regular algebra, a finite algebra. It's not called a finite algebra, we just called an algebra, because then you can just make, if you have E1 and E2, you could make E3, E4, and so on just be empty sets, and then that union. You will notice I'm not assuming that these are pairwise disjoint, because there's no reason to. We're not saying anything about the probability measure yet. Okay, so this is the definition of an algebra and a sigma algebra. And now we get to say the actual definition of what a probability space is. So here is a definition. A probability space is a triple. So it consists of three pieces of data. You have a sample space, then you have an algebra, a sigma algebra of events, and you have a probability measure, P. So this, where omega, this is just a set, non-empty set, called the sample space. Then script A, this is a sigma algebra of, I'm not sure whether you're supposed to say of omega or on omega, I'm not sure. And P, this is a probability measure defined on sets from, so not all events, but the ones that come from the algebra. We want our algebra, by the way, to be a sigma algebra for the reasons that we've said before, that we want to be able to work with sequences. So if we have a sequence of events, we want to be able to take their union and intersection and know that that belongs to our collection. So this is a probability measure defined on the sigma algebra. And I'm not going to write out what that means because we've already written it out. The only distinction is that this function P is not defined on every subset. It is defined on a smaller collection of subsets, but we insist that that smaller collection of subsets should form a sigma algebra. So intuitively, right? So maybe you can say the intuition here. We can say the intuition for what we're trying to say. So omega is supposed to represent the possible outcomes of a random experiment. Then the script A, this is like a theoretical annoyance. it does not really have an intuition to it. It's just like a necessity when you're doing formal math. But you can say that this is the events on which probability is defined. Like in real life, you never even come across bizarre subsets of the sample space for which it's not possible to compute probability because that set falls outside the event space. Maybe we can call this the event space, right? The space of events. Or maybe the event algebra, maybe that would be better, the event sigma algebra, perhaps. So A just represents those events on which we can compute probability. And again, the theme with this is that the events for which probability will not be defined are so unusual that they never really come up. Because if you think about, whenever we're doing mathematics, we usually start with simple to understand subsets. So like in our previous examples, we were looking at arcs. So it's simple to understand subsets. And by taking unions and intersections, we can create some complicated subsets out of that. But if we're only allowed to use those countable processes, then that would then mean that all of the sets we can possibly be interested in will be contained in our family. And then what is the P? The P here, this is the probability function. The probability function, because that's what a measure is, it's a function, which describes the randomness of the experiment. Because in order to describe how randomness behaves, you have to say, you have to pick one of these events coming from this algebra and be able to say the chances of every single one of those events take place. And if you have a different random experiment, then you're going to have a different probability measure, as we were saying earlier with our dice example. Now, this is interesting, but it does not really do anything. I'll make this as a comment right over here. So this is interesting, but not useful. This script A, the event space, is actually a topology on sigma, I should say on omega. It's a topology, because what's the property of a topology? A topology is supposed to consist of the empty set. It's supposed to consist of the entire set. And then if you have a bunch of open sets, their union has to be in omega. Well, I guess I should be careful. It's not exactly a topology, because with a topology, it's arbitrary unions. Here we have a sigma algebra. We have countable unions, as opposed to arbitrary unions. But in a topology, so maybe is similar. Maybe that's the way I should. It's similar to a topology. That if in a topology, if you have a collection, a finite collection, then the intersection has to be in the collection. But here we are talking about countable intersections. However, in the topology, there's no requirement about complements. So it often has more properties than a topology generally has. And sure, so it's just interesting, but it's not actually going to be useful for us. So this is the definition of what a probability space is. Okay, so let's take this down and get to an important theorem, which we're not going to prove. The proof is not very interesting, and it's fairly tedious. And as you will see, it's pretty believable. You just have to work through the details. I would first like to start with a proposition. And this proposition goes by the name continuity of probability measures. It's called continuity because it's very reminiscent of continuity that you talk about from calculus. In calculus, if you have a function, you say the function is continuous at a point if you consider the limit towards that point, and that is obtained by evaluating the function at the point. This is going to be very similar because the idea here is you're going to probability measure. It's a function, but it's not being evaluated at a real number. It's being evaluated at the event. So what we would have is we would have the probability measure is equal to the probability measure of something else. But instead of a point, we will have an event, and then we will approach an event using another event. And we're going to say that the probability of an event F would be equal to the probability of the event E as F gets closer to E. But the issue is that this is a little bit ambiguous. What exactly do we mean by that? So that's unclear. Those are events. Those are not real numbers. So instead what we do is we'll do it as follows. So there's two versions of this, and we're going to prove one and you can prove the other. So we're going to assume that omega script A and P is a probability space, and script A is a sigma algebra on the sample set omega. In general, when we talk about probability spaces, it is always assumed that this algebra is a sigma algebra as opposed to an ordinary algebra. So in other words, it contains countable unions and countable intersections. Then we have the following two properties. So the first one's going to say that if we have a family of events, En, and all of these events are in the algebra, in the sigma algebra, and these events, they converge, but to avoid confusion, we're going to say they increase towards E. So what do we mean they increase towards E? It means, in other words, that this is a nested collection. So E0 is contained in E1, that's contained in E2, which is contained in E3, and so on. So it's essentially what we want to say is a monotone sequence. You see, when you're dealing with events, they're not numbers, so they're not exactly ordered. So we cannot say what it means to get closer to, because events are not ordered. However, if you assume that they form an increasing sequence, then it kind of makes sense and say they're getting bigger, and they're getting bigger towards E. So how do you interpret that? Well, you would interpret E as the supremum of all of those. So the sensible way to do it is then E is the union of all of those events. And E is the union of all of those events. So it's a limit of those events. This is why you need it to be a sigma algebra, because we know that the ENs belong to our algebra, A, and this is a countable union of events in the algebra. So because this is a sigma algebra, the countable union is in the algebra as well. So this is why it's important that it's in the algebra. So then, if you calculate the sequence, so this is now a sequence of real numbers. These are events, but when you apply the probability measure to the events, you're getting a real number between 0 and 1. And this will be a sequence of real numbers, and the sequence will increase, so it's a monotonically increasing sequence, and its limit is the probability of E. Okay, so this is the first version, and the second version is almost, well, it's almost identical to it. It's just with the decreasing version. It says that if En is a family of events in your algebra, and this sequence decreases down to E. And I'm not going to write out what that means. You can guess. It means instead of these one contained in the other, this one contains the former. And then the limit, E in this case, would be the intersection of all of them, which is again in the sigma algebra. So then the probability of all of those events has a sequence of real numbers that will now decrease down in the limit to the probability of E. So this is called continuity of probability measures, and it makes sense why we call it, because it's very similar to how functions behave. So for the proof of this, we're going to say that part 2 follows from the first part. And this is going to be a homework problem for you to figure out. So we'll just prove part 1. Okay, so how do we prove part 1? So here's how we're going to prove it. Let's draw a picture. So here's E0, and then E0 is contained in something larger. We call this E1. And then this is contained in something larger called E2, and so on. So this is an increasing family of events. Now, what we're going to do is we're going to look at these rings that are being formed. So let's set F0 to be E0. We're going to set F1 to be the ring in between E0 and E1. So in other words, all of this is what we're calling, this is what we're going to be calling F1. So in set notation, this is going to be E1 take away E0. And then F2 is going to be this ring in between them. So this is going to be what we call F2. So F2 will be E2 take away E1, okay? And so on. So in general, Fn would be En take away the previous one. Of course, we have to make the exception when n is equal to 0. That's the exception. Then we just interpret that to be the empty set. So we have these events. Now, you can make this a rigorous proof, but I'm not going to do this because I think the picture is a lot more intuitive. You can, of course, turn it into a more rigorous proof. But we have, and I think this is fairly easy to see. You can see it very easily in the picture, but you can make it rigorous, but that's kind of boring. So we have that this family of events are pairwise disjoint. All of these belong to your sigma algebra A. And when you take the union of all of them, you're stacking all of these rings together. And when you stack the rings together, you're just taking the union of all of these E's. It's just the thing is, you see, when you take the union of all of these E's, you have a lot of redundancies, because when you move from E0 to E1, you're already including E0. So by writing it in this form, you're removing the parts that you already counted. So the union of all of these sets will be the union of all of the E's. So that would be equal to the union of the E's. But the union of the E's is equal to, by definition, it's equal to just E. E is the limit set of all of them. Okay, so now we use the fact that we have a measure. So thus, since probability measure is countably additive, and this part is going to be important, it's countably additive on disjoint unions, we have that the probability of E is the sum of the probability of Fn. Now, to make this a little bit easier to see, when you're talking about an infinite series, you have to recall what that means. It means you look at the partial sum, and then you consider what happens as you make the partial sum longer. So this is just equal to, this is really by definition of the infinite series. This is the limit when, let's say, capital N goes to infinity. And then this is the sum from lowercase n to uppercase n. And it's the probability of these. I think if you rewrite it in this form, it will be easier to see what is going on. But now let's rewrite what these are. This is so we will have that this is the limit as capital N goes to infinity. And now we rewrite what these are. You have to understand that the Fn is equal to this. It's En take away En minus 1. So in particular, it would mean that the probability of Fn is the probability of En minus the probability of this one. So I leave that for you to think about. That just follows from the properties of the measure. That's not difficult to see. So this would be the probability of En minus the probability of En minus 1. And of course, the convention here is that if n is equal to 0, then E subscript negative 1 is interpreted as the empty set. That's the only way to interpret that. But this is what we call a telescoping sum, which basically means if you write it out, you have a lot of cancellation. So just to show you what I mean, if you have E3 minus P of E2, and then you add P of E2 minus P of E1, and then you add P of E1 minus P of E0, and then you add P of E0 minus P of the empty set. So this is what would happen if you were to write out the sum up to capital N equal to 3. And you can see that this is a telescoping sum, so all of this goes away, and you're left with the probability of E3 minus the probability of the empty set, but the probability of the empty set is 0. And so we have that this becomes the limit as capital N goes to infinity, and we're just left with the probability of En. And that completes the proof. We have shown that the probability of the sequence of events converges to the probability of the limit event. So if we go back to the statement, this is what we claimed. Now you might complain and you might say we never proved that this sequence is monotonically increasing, but that part is trivial because these events are increasing. The larger the event, the larger the probability. So this is what we call the continuity of probability measures. This is a nice fact to know in general. And now I want to get to a technical theorem that we're not going to prove. This is a technical theorem in measure theory. If you're wondering what measure theory is just like probability. Well, I should say that's the way it begins. It begins exactly just like probability theory. But in probability theory, you have the requirement that a probability measure, when you evaluate it on the entire sample space, it has to give you 1. Whereas a measure in general does not have to give you a number when you evaluate it on the entire sample space. It does not have to be 1. It could be any number from 0, including positive infinity. So you allow it to be positive infinity. So that's really the distinction between a probability measure and a measure. So this is a theorem in measure theory, but we're just going to adapt it to what we're doing. And let me just maybe say the goal of this theorem. So the purpose of this theorem is it allows us to construct probability spaces by first constructing probability spaces, or you can say probability measures, on algebras instead of sigma algebras. So you want to think of an algebra as being easy. It's something that's easy to understand. And a sigma algebra is something that is hard. Okay, so to use an example, let's go back to the unit circle. This was our sample space. And we can let A0, this is going to be the algebra of arcs on the circle. So what is the algebra of arcs? Well, to put it simply, it will contain arcs. So an algebra is a collection of subsets. So you will have an arc. The arc could be open, it could be closed, it does not matter, but it will contain an arc. And you can see that if you take the complement of the arc, right, the other side, you still have another arc. So the complement of an arc is an arc. If you have two arcs, right, if you have two arcs and you intersect them, the intersection will either be empty, in which case it is automatically in the algebra, or it intersects, but if it intersects in another arc. So the intersection of two arcs is another arc. Okay, but now the union of two arcs is not necessarily an arc. So you can have an arc over here, and if the arcs intersect, then that gives you a larger arc. But they do not have to overlap. But then you have two disjoint arcs, and their complement is another two disjoint arcs. So the algebra of arcs, this is simply the collection of finite amount of arcs. That forms an algebra. That will form an algebra for you. It does not form a sigma algebra, because the moment you have infinite collection of unions and intersections, things get very complicated. So later on, we're not going to do it, so we will not do this in this lecture, but we can construct a Cantor arc. So instead, as a similar example, in a future lecture, we will construct the famous, if you ever heard of this, the Cantor set, if you ever heard of that. And this is sort of a similar idea. It's just easier to do this on the real line instead on the circle. It's just the notation is easier, but it's the same idea. You can construct something called the Cantor arc. And the Cantor arc is no longer a finite union of arcs. It is something that's a lot more complicated. Another thing you can imagine is if you have a single point, that is an arc. That's what you call a degenerate arc. But then you can have another point. You can have another point, another point, another point. And if you have a countable collection of points, that will give you something in the sigma algebra, but it's not in the algebra. It's not a finite amount of arcs anymore. So the algebra is a lot more complicated. I'm sorry, the sigma algebra is a lot more complicated. The algebra is easy to understand. But when we do probability theory, as we explained, we want to have sigma algebras and not algebras. So the point of the theorem that we're about to say is that we want to focus on algebras, which are easy to work with, and we're going to define a probability measure on the algebra. And then the theorem, we're going to activate the theorem that will then tell us it is possible to enlarge the algebra into a sigma algebra so that the properties that you had, they continue to hold. That is really the point of this theorem. So it's like one of those existence theorems. Okay, so, and if you let script A, this is the sigma algebra generated by all arcs, then this is something that's hard to understand. The sets can be very, very bizarre. So let's therefore write down what the theorem says. So this goes by the name of the Carathéodory extension theorem. Let omega A0 P0 be a probability space with A0, this is an algebra. Okay, so we're assuming we're starting with an algebra. Technically, it's not supposed to be a probability space. I think there are some people, depending on the authors, they might call it a pre-space. So it's not yet a probability space. It's right before that. And the Kara-Theodori extension theorem says that under certain conditions, and there's many equivalent conditions. So depending on which book you use, they might write it a different way. I'm going to show you which I think is the easiest one, the one that I think is the easiest one to check. But if you look at other books, they might say other things. So under certain conditions, we can enlarge, there exists a probability space so the same sample space, but now you have an algebra and you have a probability measure on the algebra. So by the way, I should have said this, I forgot to say this, but we're assuming that P0 over here, instead of being countably additive, which would not make sense because this is not a sigma algebra, we're rather assuming that P0 is additive on disjoint unions. So there exists a probability space. So now this P has the stronger property of being countably additive on disjoint unions. So you can enlarge this. There exists a probability space with the original algebra being contained in this sigma algebra. So this is now going to be a sigma algebra. And you also want to say that this probability measure is exactly that probability measure, except it's now defined on the larger family of events. And if you pick an event that belonged to the original algebra collection, then the way you calculate the probability using this enlarged probability measure is exactly the way you do it using the original probability measure on the algebra. So under certain conditions. So maybe what would be helpful is I show you the Wikipedia page on the Kara-Theodori extension theorem. And then we can talk about the different conditions that one has. We're not going to talk about the proof of this. It's a long proof. There's many things. And then you basically, what you do is, I'll give you the outline of how you do it. You use P0 to create something called the outer measure on every subset. So you go from A0 to the power set. So you enlarge, you go to the extreme case by looking at every possible subset of omega. So you start with your sigma algebra is the power set. So that's sort of extreme. And then instead of P0, you come up with a new function which you call the outer measure. But then you pick the sigma algebra is then constructed to be the collection of events that satisfy some desirable property with the outer measure. And then there's a lot of things to check. You have to check that that collection of special events, they form a sigma algebra, they contain the original one, they satisfy those properties, the P is then a measure. So there's so many things one has to check, and the proof is very long. And that's something that's appropriate in a probability theory part 1 class. You can also say maybe you do it in a measure theory class. But to show you what the theorem says, I like to think of this theorem as sort of the equivalent of the real numbers. When you first learn advanced calculus, you often accept the fact that you have the real numbers and then you use them to do advanced calculus, real analysis. So this sort of plays the same role, that it's technical, but it has a purpose that it tells you that what you're doing makes sense. So in measure theory, the Kara-Theodori extension theorem states that any pre-measure, so they call it a pre-measure, defined on a ring of subsets. So instead of calling it an algebra, they call it a ring of subsets of a given set omega, can be extended to a measure on the sigma ring. That's what we call the sigma algebra, generated by R. And furthermore, this extension is unique. There's exactly one way to do this. If the pre-measure, so this is what we're calling P0, is sigma finite. For our purposes, a probability measure is automatically sigma finite. We're not going to go there. Okay, so here's the statement. several very similar statements of the theorem can be given. So this is what we were saying, that there's different conditions. So you can use greater generality, which I do not want to do because it just makes things a lot more technical. I'm trying to keep it as intuitive as possible. So there is something called a semi-ring of sets, or a semi-algebra of sets, and you can do it like that. That's a more general version, but I do not want to go there. So they say let sigma 0 be an algebra of subsets of X. And then you're going to have a function. This is basically what we're calling P0. That's like our probability measure. It takes a set in sigma and it assigns it to, so we are assigning it to 0 to 1, but in measure theory you can assign it from 0 to infinity, which is finitely additive. Okay, so this basically means it has the property of a probability measure, that the probability of a disjoint union is equal to the sum of the probabilities, right? So this is a disjoint union. And this function has to satisfy an extra condition. And the extra condition is, okay, so this is the way that they're writing it. I think this one is a bit more confusing, but let's skip this. I'm going to show you an easier way to restate this. Okay, so there's some comments here. So this theorem is remarkable for it allows one to construct a measure by first defining it on a small algebra of sets, where the sigma additivity, so the sigma additivity is referring to the fact that it's additive on disjoint unions, can be easy to verify. And then the theorem guarantees the existence of its extension to a sigma algebra. So do they have any other versions? So they give you a proof sketch. This is sort of the outline of the proof, but it's not that long, but every one of those little things, there's so many little things to verify. So I think that would be enough for us. So I'm going to show you one of the equivalent conditions that you can use. So one of the conditions is that under certain conditions. So one of those conditions would be this, that P0 is continuous. And it's enough to show that it's continuous at the empty set. If it's continuous at the empty set, it's not difficult to show it's continuous everywhere else. So what does this mean? I.e., if you have a collection of events, so you can either show it's continuous at the empty set or continuous on the entire sample space. So let's say it's continuous on the entire, it does not matter. Let's say it's continuous on the entire sample space. So what does that mean? I.e., if we have En, and these are events in the algebra, and the ENs, this is an increasing, they're increasing to omega, then the probability of En, that this sequence of numbers has to increase as a sequence to 1. Probability of omega, which is 1. So that's what it means to be continuous at the sample space. Okay? Continuity. The reason is it actually makes a lot of sense. I should say instead of P, I should see 0. The reason should make a lot of sense because that's the proposition that we just proved. If you have a probability space is continuous at any event. So in particular, it is continuous. If you choose the event to be everything, it's continuous at omega. What does that mean? That means if you have an increasing family to omega, then the probability of all of those events in the limit should converge to the probability of omega. If you have a probability measure on a sigma algebra, continuity must be a necessary it must be a necessary property. And this necessary property, which follows from any probability space, turns out being sufficient. It's also a sufficient condition to assert that there exists an extension. And this extension is furthermore unique. There's a unique extension. So this is the Kara-Theodori extension theorem. We'll just state what the theorem is. And I like to show you how you would use it in the example that we're doing by working on our circle. That's our motivating example on the circle. So let's go back to the circle. And explain how you can then use this theorem to construct a probability space on the circle. Let us conclude this lecture, and this lecture has become a little bit too long. But anyway, let us conclude this lecture with an illustration of the Carathéodory extension theorem. And what we're going to do is we're going to carefully construct a probability space. So probability space consists of a sample space, a sigma algebra, and a probability measure that intuitively models the random experiment of spinning a pointer on the unit circle. So now we are in position to go through the steps to show how you create such a probability space. So what we start with is the sample space is very simple. That's just complex numbers whose norm is equal to 1. And we're going to let A0, this is going to be the algebra generated by all arcs of the circle. Now, because this is an algebra, it's very easy to understand an element of this one. So A0 is, what is it? So an element, maybe I should say an event in A0. I mean, an event is just a set, but an event in A0 is an arc or a finite union of arcs, right? So this is your circle, and if you have an event, it's either an arc already, because it's the algebra generated by all arcs. Now, if you have two arcs, and they happen to intersect, then you can see their intersection is an arc, which is back in the algebra. However, if you have two arcs, oh, and I should also say if two arcs intersect, then their union is an arc, and it's also in the algebra. But of course, the reason why we're saying that you need to consider finite union of arcs, maybe we can say a finite disjoint union. Because if the arcs intersect, then their union is just a larger arc. But if the arcs do not intersect, then if A0 was only the arcs, then that would not form an algebra because the union of two events is not in the event. So you have to slightly enlarge A0 to also include finite unions of disjoint arcs. So that's a very simple algebra to understand. And it is easy to see. Okay, let me take this back. So if E is an A0 and E is an arc, it does not have to be an arc. It could be a finite union of arc, but let's say it is an arc. We define P0 of E. The idea is that before we can define the probability measure on the sigma algebra, we first define it on the algebra where it's easy to understand. So we're going to define P0 on an arc to just be the length of that arc divided by 2 pi. Okay, if E is a disjoint union, so you can write this, some people write the disjoint union like this. From the index goes from 1 and n of EI, and EI are arcs. Because in general, the E is not an event in A0, as we said, is not necessarily an arc itself. But if it is a disjoint union of arcs, then we define P0 of E. It has to be defined as the sum, because it's supposed to be a probability measure. So this is forced on you. Now, you can see why this is very convenient when you're working with an algebra. You have a finite collection, and the events are arcs, where it's very easy to define what you mean the probability of an arc. Okay, and you have to verify. So we need to verify that P0 is I'm not sure if you can call it a probability measure. I'm not sure what the actual vocabulary is, but I'm going to abuse notation in case I'm not saying it correctly, is a probability measure on A0. So as I remarked before, this is a bit problematic because, strictly speaking, whenever we talk about measures, we talk about measures being defined on sigma algebras and not on algebras. So we are slightly abusing terminology, but let's verify that it's a measure on an algebra rather than a sigma algebra. So what do we have to see? Well, clearly, if E is an A0, then its probability would be between 1 and the empty set. I'm sorry, 1 and 0. The reason for this is, I mean, it's certainly true if E is, I guess it's not super trivial. I mean, it's easy to see geometrically, but maybe proving it formally will take a bit more work. But basically, if you have an arc, then obviously the probability of the arc is between 0 and 1 because the length of the entire circle is 2 pi. So that's not a problem. But then you can say, well, what if the arc is a disjoint union of arcs? Then how do you really know that they have to be less than 1? So that takes an argument. Maybe I should remove clearly. Maybe I should just replace it by visually. So it's easy to see this visually because if you have one and then you have another, and they do not overlap, then their sum, the sum of their lengths, has to be less than 2 pi. I mean, this is like one of those things which is very easy to see intuitively because you are talking about lengths and things like that. But how would you prove that more rigorously? Well, that's going to take more work. And I really do not want to go there. Like, it's not really the purpose of the class. We want to just illustrate the idea of how this works. You can think about how you would justify that more rigorously if that bothers you. And then, and also, if E and F are in the algebra and E and F are disjoint, then the probability of their union is going to be the probability of their sum. So how do you prove this? Well, without loss of generality, we can assume that E, F, and the union are arcs. The reason for this is because if E is not an arc, then it is a disjoint union of arcs, and so is F. And then what you would do, yeah, so if E and F are not arcs, then they're disjoint union of arcs. And then you just apply the argument, and then the probability of E and the probability of F would then be a sum of the probabilities of those individual pieces that make it up. So because of this, right, as you can see, if the event is not an arc, it's the sum of the probabilities of the arcs. So that allows you to reduce everything down to arcs. So then you just have to consider what happens if they're arcs. So then, I mean, this is, again, one of those things that is easier to see in a picture. Proving it more rigorously without a picture will take more effort, but basically this is E. And now if the F, now we're saying E and F are disjoint. So in fact, this feels more like a topological proof because you are talking about their boundary. And that's why I do not think it's appropriate for this course, because this is not a course in point set topology, but it feels more like a topological proof because you're talking about like the endpoints and the limit points and their boundaries and how close they get together. But the idea here would be that if E and F happen to be disjoint, then the probability of the union is automatically the probability of their sum, because that's the definition. When their union is a disjoint union of two arcs, and the probability of a disjoint union is the sum of the arcs, just by definition of how we constructed this. So you have to really consider the case, what happens if their union is disjoint, but it becomes an arc. So that would happen, for instance, that maybe F is like open at that endpoint, and then F gets filled in at that endpoint. And then the union is disjoint, but it is still an arc. And you can see from this picture that if you wanted to find the length of their union, clearly, at least visually, it's not hard to see that it would be the length of E plus the length of F. And then from there, it follows that we have verified this property. Should have written this property using P0. But that's not all we have to do. In order to use the Kara-Theodori extension theorem, we now have to verify that, the continuity property. So if we were permitted to use the Kara-Theodori extension theorem, then we can enlarge our algebra, our probability space on an algebra, to a probability space on a sigma algebra, so that this is the sigma algebra generated by all arcs. And this is actually very complicated. I did allude to this earlier in the lecture, but there is something called a Cantor arc. Usually you draw it not on the circle, you draw it on the real line. And I'll probably construct that for you in the next lecture, because this lecture is becoming a little bit too long. But basically what it is not a countable set. All right, it is an uncountable set. So in particular, it is not a countable union of points. Points happen to be arcs. They are degenerate arcs. They are arcs of no length. And if you have a sigma algebra, then that would be a countable union of points. So you could have, for instance, going back to your circle, you can just take a countable collection of points all the way on the circle everywhere like this. And that would be an event in the algebra. But it's sort of like a union of points. It's not that hard to understand. But the Cantor arc, it's an uncountable set. So it means it's not a union of points. I mean, of course it is a union of points, but we always talk about countable unions. So it's not a countable union of points. Nor, and this is the really strange property, nor is it a countable union of arcs. Countable, maybe I should say disjoint union or whatever. It's not a union of arcs. As we will see, it does not contain any arc. A non-degenerate arc. A non-degenerate arc does not sit there. So it means it's something that is, you would say, genuinely new. That it's a very bizarre type of a set that is not describable by using arcs anymore. And that's because you're using infinitely many things. By using a countable collection and doing something with it, you can generate some very strange sets. Okay, so this becomes rather complicated, and the Carey-Theodori extension theorem says that it is possible to construct a measure. Now, you cannot construct a measure by using length anymore, because length only makes sense if you have an arc, so then you can kind of talk about what we mean by length. But for a more complicated type of a set, that no longer makes sense. So that's why we have to use the extension theorem. So I would say that we can enlarge our algebra into a sigma algebra, so that it's still going to be generated by the arcs, but it will be a sigma algebra. So all possible sets that can be generated using a countable process of unions and intersections over and over and over again by using these arcs. And if E is an arc, so if it's like a special event, a very easy to understand event, then the probability of that event can be easily described by using the previous probability measure, or maybe pre-measure, whatever we call it. And the way you calculate that one is by using length. So you calculate it by using length in the case when it's a simple event, like this. But the fact that such an algebra exists and it has this particular property is something that is by no means obvious anymore. But that's the way that it works. So now notice we're saying if we were permitted. And the point of this illustration is to show how the Carey-Theodori extension theorem is used. So we have to justify why are we permitted. So the question here is, why are we permitted to use the theorem, this theorem? So there is a hypothesis that this theorem has. And that hypothesis is we need to check that, and you can do this with either unions or intersections. I'm going to do this with intersections. So we need to check that if we have a collection of events in the algebra, notice it's the algebra, not the sigma algebra, because we want to go from the algebra to the sigma algebra. So if we're in the algebra and En are decreasing down to the empty set, then the probability of En, then the limit of the probability of these Ens would be equal to 0. This is what we call continuity of measure. Probability measures are continuous, and I wrote P0. I meant to say P0, of course. So this is what we have to verify. So for simplicity, we can assume, so this has to do again with the fact that every one of these E's is a disjoint union of arcs. So we can reduce everything back to arcs. We can assume that each En is an arc. So thus, we have a decreasing collection of arcs. So these are what we call nested arcs. So you have your circle, and on the circle you have an arc, and then within that arc you have a smaller arc contained within that one, and then you have a smaller one contained within that one, and a smaller one contained within that one. So these are diminishing arcs. They're getting smaller, and when you intersect all of them, they give you the empty set. So you therefore have to argue that this property will be satisfied. So I think maybe what would make sense here is I'll give you the outline for the proof idea, and you'll do it yourself. So this is an outline of the proof, and you finish it yourself. So first, we can map this problem onto the real line where it becomes easier. So basically, you're mapping this to the real line. How do you map it? Well, let's say this is the point which is missing, so you cut it at the point and you open it up. In fact, you can map it to the interval from 0 to 2 pi. So let's say this is the point which is missing. Every point on the circle can be described in the form I theta. So without loss of generality, we can assume that 0, so this complex number, I'm sorry, not 0, e to the 0, so 1. So when the angle is 0, we can assume that this point is the missing point on all. I mean, there has to be a missing point because the intersection is empty. So there has to be a point where the arcs do not have in common. And if the first arc, E0, contains everything, then you just skip the first arc and you go to the next arc, which will miss a point. I mean, eventually, if you go far into the sequence, you can begin it at E0, right? You can assume that E0 begins at some point that omits e to the 0. So you can, without loss of generality, you can assume this is missing. And then you would just map these arcs. You would map that onto the interval, and then you basically have a picture where you have an interval, you have an interval, you have another interval sitting inside that, you have an interval sitting inside that. And if you've seen this before, this is a very common situation in an advanced calculus course. You call this the nested interval theorem, something along those lines. So when you map this onto, we can even just assume onto, let's say, 0 to 2 pi, where the problem becomes easier. So namely, we have a collection of intervals. These are intervals, and their intersection is empty, and we want to show that the limit as n goes to infinity of the length of each interval of their lengths will go to 0. That's basically what you have to show. So the idea is that every one of these intervals, it's either an open interval or closed interval that includes the points or not. So I'm going to write it like this. This is going to look very funny, but you'll see what I mean. So it has a left endpoint and it has a right endpoint, where the left bracket is chosen from either the open bracket or the square bracket. And the right bracket, which we're calling by a triangle, is chosen from this one or that one. So that's some very funny notation, but I think you know what I mean, right? So I'm just saying that this is, you're either including or excluding the left bracket, or you're including or excluding the right bracket, because this is how an interval is going to look like. And then you have to observe that since these intervals are decreasing down to the empty set, we have that the left endpoints are going up and the right endpoints are going down. Okay, so just to show you a picture, if this is A0, B0, then this is A1, B1. Notice, because the interval sits in the previous interval, the right endpoint gets bigger, whereas the left endpoint gets bigger and the right endpoint gets smaller. So these are monotone sequences, right? These are monotone bounded. They're bounded because they're on the interval from 0 to 2 pi sequences. So thus, they have to converge. So thus this converges to A, and this converges to B for some A and B between 0 and 2 pi. Okay? And you basically, oh, and furthermore, the left endpoints are always smaller than the right endpoints. So hence, the limit of the left endpoints is always smaller than or equal to the limit of the right endpoints. And what you're going to show is you're going to argue that if A is equal to B, then the length of IN is equal to BN minus AN. That's how you find the length, right? You subtract the endpoints. But in the limit, as n goes to infinity, this is going to be B minus A, which is 0. And that's exactly what you wanted to show. You wanted to show that the lengths of the intervals in the limit goes to 0. If, however, A is strictly smaller than B, then choose any C that's between A and B, and argue that this C will then be in the intersection of all of them, contradicting that C is in the empty set, because the intersection of all of them is the empty set, and that's not supposed to happen. I meant to say 0 to infinity. So that's like the outline. That's what you have to work through. So this means that we're permitted to use the Carathéodory extension theorem, and as a result, we have constructed a very rigorously defined probability space that models the random experiment of spinning around a pointer. I should say, if you're worried about this, if you look at this and you say it's very difficult to show that a probability measure, a probability space exists for a random experiment, a lot of the times there are tricks that you can do to avoid going through this entire tedious process to show that it exists. And also, a lot of the times people might just assert that you construct such a probability space without going through the details all over again. That's normally what we would do in most cases. We would just say there exists such a probability space because of the Carathéodory extension theorem, and we just accept that we have it so we can use it to do probability. So this will conclude this very first lecture. At the end of this video, you will see some problems for you to work on, and then we'll continue with probability measures on the real line in the next lecture.